Welcome back. And as we begin to look at the substitution reactions, we're going to start off with the Sn2. And we're going to look at the mechanism, okay, because we've already learned a few things about what an Sn2 is. S stands for substitution, N stands for nucleophilic, 2 stands for the reaction is second order. That is, it depends on the concentration of the reactant as well as the concentration of the nucleophile, right? All right, so here we have our basic reactant, which contains the substrate and the leaving group, and you also got your nucleophile, which in this case is OH minus, right? So we are using a negatively charged ionic nucleophile, right? Now, as I said, the substrate primarily is the carbon that contains the leaving group, and that carbon here happens to have 2 hydrogens. So it is a primary carbon substrate, right? And we know primary carbon substrates are substrates that leads to an Sn2 mechanism, right? So what does this mechanism actually looks like? Your nucleophile attacks the carbon containing the leaving group, and as it begins to attack the carbon that contains the leaving group, or in other words, as it attacks the carbon, the leaving group begins to come off. It's kind of considered, means it happens simultaneously. As the nucleophile attacks the carbon, the leaving group begins to leave, right? So it's a simultaneous reaction. So Sn2 reactions are simultaneous. That is, you will see it, what I'm talking about when we get to Sn1. Okay, so Sn2 reactions are considered, means the attack of the nucleophile and the departure of the leaving group all happens at the same time. Now pay attention to the 2 hydrogens with the open wedge and closed wedge shaped. Pay attention to that, okay? All right, so this is where we start, where we end. This is called a transition state. All reactions have a transition state. Whether they have an intermediate or not is a different story. But all reactions go through a transition state. That is, that a transition state is nothing but where a bond is formed and a bond is broken. So you can see that as the OH tries to make a bond with the carbon, the bond between the carbon and the bromine, which is the leaving group, is getting broken at the same time. So that is a transition state where a bond is being formed and a bond is being broken, okay? Which happens in almost every chemical reaction, right? Every chemical reaction involves bond formation and bond breakage. So almost all chemical reactions involve a transition state. But just because all reactions involve a transition state does not mean all reactions would have an intermediate. Now, Sn2 reactions, because of it being considered, that is, bond breakage and bond formation happens at the same time, it does not have an intermediate. So Sn2 reactions are considered reactions, and it only contains a transition state. So a transition state is very, very short term. Like, I mean, it doesn't last very long, means you cannot isolate it. It just happens so quickly that the bond between OH and carbon is formed and the bond between carbon and bromine is broken, all very quickly, okay? So what happens then? As I said, pay attention to the wedge bonds, the open and the closed wedge containing the 2 hydrogens. See what happens. What do you see is happening? You see that the open wedge has moved to the other side, right? So now this is called inversion of configuration. Say if you were to do, well, first of all, this is really not a chiral carbon, is it? But say, I'm saying, the reason I wanted to keep it simple here is just for you to see that it leads to an inversion of configuration, right? Now, this is technically not a chiral carbon, right? Right? It is not a chiral carbon. So we can't really talk of R and S here, right? But what you see is, say if you did had a CH3 there, you'd still have an Sn2 because that is still a secondary carbon. The secondary carbons favor Sn2 because secondary carbons are carbons containing the leaving group and one hydrogen. So in that case, you'd be able to talk R and S because you'll have 4 different groups attached to the carbon. Currently, this carbon, as it's shown here, is not even a chiral carbon. So we can't really talk in terms of R and S. But if it were to be a CH3 or some other group, then it would make more sense. But what I really want you to take from this is that Sn2 reaction leads to inversion of configuration. That is, if you start with a R, you end with an S. If you start with an S, you end with an R. So let's summarize it. You know, rate equals K times reactant times your nucleophile concentration. Because it's Sn2, it depends on the concentration of both the reactant and the nucleophile, so it is second order reaction. Right? We've already looked at it earlier when we were talking about some of the basics of substitution and elimination reactions. Sn2 reactions are second order. Let's summarize everything about an Sn2. Okay? Consider that is attack of nucleophile and departure of the leaving group. I will correct it in the upcoming versions. It should say attack of nucleophile and departure of the leaving group, not nucleophile here. Leaving group occurs simultaneously. It's second order, only transition state and no intermediate formation. As I said, all reactions carry a transition state, but do all reactions have an intermediate? The answer is no. Some reactions have both transition state and intermediate. All reactions have a transition state, but all reactions do not have both transition state and intermediate formation. Okay, inversion of configuration, that is, if you start with an R, you'll end with an S. If you start with an S, you'll end with an R. So this is all key components pertaining to an Sn2 mechanism. Moving on. Before we actually learn Sn1, we need to learn something very, very important. And I guess I could have brought it up as a separate thing, but Sn1 mechanisms commonly involve formation of something called a carbocation. What is a carbocation? Carbon attached to 3 bonds and a positive charge. Okay. So if you started with a methyl, which is again carbon containing 3 hydrogens and a positive charge, that's a methyl carbocation. Say you started with a primary substrate, that is a carbon containing the leaving group and 2 hydrogens, then that would contribute to a primary carbocation, because a carbon containing 2 hydrogens, 3 bonds of which 2 of them is hydrogen and a positive charge, is a primary carbocation. A secondary carbocation is a carbon containing 3 bonds, 1 of them is a hydrogen, and you have a positive charge. A tertiary carbocation is carbon containing 3 bonds, none of them contains a hydrogen and a positive charge. Now, why is a carbocation important? Okay, we could have had a carbocation for Sn2, but it doesn't. Why? Because of this. The tertiary carbocation is the most stable. Your methyl primary and secondary are not that stable. Even though it seems like secondary and tertiary are right next to each other, there's a difference that's equivalent to day and night. So your tertiary carbocation is of higher stability compared to your methyl carbocation, which is why Sn1 reactions are almost exclusively dedicated to substrates containing tertiary carbons, right? Remember I said tertiary carbon substrates are exclusively dedicated to Sn1. Why? It's because tertiary carbon substrates can lead to tertiary carbocation formation, which in turn is a key to an Sn1 mechanism. Okay. Now let's look at the actual Sn1 mechanism. Say you have a tertiary carbon substrate, like you see here, the carbon containing 3 bonds and a leaving group, neither of them are hydrogens, so that's a tertiary carbon substrate. So in an Sn1 mechanism, you do have the formation of an intermediate. Now, how does that work? Your leaving group comes off first, which leads to the formation of a carbocation. That's your intermediate. Okay, so Sn1 reactions does involve both intermediate and transition state. I'm not going to show you the transition state here explicitly, but I'll explain where you can see the transition state. So Sn1 reaction involves the formation of an intermediate. What is the intermediate? It's the carbocation. It's a tertiary carbocation. How do I know it's a tertiary carbocation? I just explained in the previous slide that a carbon containing 3 bonds, neither of them are hydrogens, and it contains a positive charge. That's the most stable carbocation you can ever have. That's why Sn1 reactions involves the formation of tertiary carbocation, because Sn1 reactions are exclusively dedicated to carbon substrates that are tertiary in nature, right? Okay, once you've, obviously your Br has come out, so it'll have a negative charge. Now the carbocation reacts with the nucleophile. Now this is the transition state. Now it could attack from the same side where the Br left, or it could attack from the opposite side like in Sn1. So this is called a backside attack. So the Br left from the other side. So the OH minus could attack the opposite side. In that case, you will have an inversion of configuration, right? You see the CH3 is now on this side, or it could attack the side from which the Br left, which is called same side attack, which could lead to retention of configuration. Okay, so when you have a carbocation, you have a 50% chance of inversion in configuration and a 50% chance of retention in configuration. If it attacks the opposite side from where the Br left, that's called backside attack, and it leads to retention of configuration. Okay, let me go back so I can show you one more time. This is called a backside attack, and when normally backside attack involves inversion of configuration, which is what you see, that the open wedge has moved to the other side. Now, if it attacks on the same side where the leaving group has left, that's called a same side attack, and that leads to retention of configuration. So with the, say you started with an R, and you have a same side attack that leads to the formation of an R because of retention of configuration. Say you started with an R and the nucleophile attacks the backside, then that leads to an inversion of configuration, so you will have an S. Now with the Sn1, you cannot really control retention over inversion or inversion over retention. They both kind of occur equally, so you'll have a 50-50 product. That is, you'll have a 50% retention product and 50% inversion product, right? So with an Sn2, it's purely inversion. With an Sn1, you have inversion and retention, both are possible. Sn2 does not involve a intermediate. Sn1 does involves the formation of an intermediate. Sn1 is two-step process because you form the intermediate, and the intermediate then reacts with the nucleophile. So Sn1 is two-step process. Sn2 is one-step process. That is, it's conceded. So everything happens at the same time. The attack of the nucleophile and the detachment of the leaving group all happens at the same time. So Sn2 is a one-step process. Sn2 is a two-step process. Sn2 is a one-step process. Sn1 is a two-step process. And Sn1 involves the formation of an intermediate. Sn2 does not involve the formation of an intermediate. Okay, so Sn2 as inversion of configuration, Sn1 is inversion and retention of configuration. So I'm going to summarize. So the rate law would be rate equals just concentration of the reactant. It does not depend on the concentration of the nucleophile. So Sn1 reactions are first order reactions. So Sn1, it should read Sn1 reaction summary. So it involves two steps, the carbocation formation and then the nucleophile attacks it. Sn1 reactions or first order reactions contains an intermediate, an inversion and retention of configuration, as we see in the two figures up there. All right, so the next video I'm going to come back and talk to you about E1 and E2 elimination reactions. So stay tuned.